The original author of Wireshark is Gerald Combs, but many of you may be familiar with it under its previous name, Ethereal. How did Ethereal get started? Well, back in 1997, when Gerald Combs was working in the IT department at the University of Missouri in Kansas City, he was dragging around a sniffer portable. And when he went to a new job, they didn't have the budget for a sniffer system, so instead he was just using TCP dump and Snoop on his Linux and Solaris boxes. But those tools didn't provide him with the interface that he wanted. So in 1997 he began working on Ethereal, and eventually it would release in August of 1998, the first version number being 0.2.0. A lot changed in 2006. In June of 2006, Gerald moved to work with Case Technologies. And when he moved to work with Case Technologies, he couldn't take the name Ethereal with him. So Wireshark was born. So in June 2006, that was the first time we saw the name Wireshark, and the announcement was released that month. All of the developers that had previously worked on Ethereal also moved over to start work on Wireshark. In March of 2007, Wireshark University was founded. I'm on the Case Technologies website, which is www.casetech.com. And you may know Case Technologies through its development and promotion of WinPCAP, as well as Wireshark, and its release of AirPCAP, which is the wireless network adapter that we can use with Wireshark on a Windows system. I've opened up my Wireshark Network Analyzer right now, and if you would like to see the list of developers, you can click Help and then About Wireshark. Now this has more information than a normal About window would. First of all, you'll see the basic information about your Wireshark system, and this is how you can see what version you're currently running. In addition, if you're running on a Windows system, it will define which Windows OS you're running on, what the service pack and build are, and the version of WinPCAP that you're running. If you have AirPCAP installed, it will also denote that on this window. You'll see that it mentions that Wireshark is open source software released under the GNU GPL, and it gives you the link to the main Wireshark webpage. This is also where you can find the list of authors. And as you scroll through here, you'll see there are a lot of people responsible for building Wireshark and maintaining it and making it as strong as it is. This is also where you will find out where the folders are and where the various elements of Wireshark are located on your local system. In addition, many of the dissectors, which are basically the decode pieces for Wireshark, are maintained as plugins, and here you can find the plugins list. Finally, you have the License tab, and this provides you the information on the general public license for Wireshark. You can also find this information online at Wireshark's webpage, which is www.wireshark.org. In the next module, we're going to look at how Wireshark works. Let's talk about how Wireshark works. And understanding how Wireshark works will help you understand how other analyzers work as well. The names may be different for the various components, but it's still basically the same type of functionality here. We're going to start talking about how we capture traffic off of the cabling system, and then we'll talk a little bit about what happens when we just open up a trace file from the local drive. So first of all, we're connected into a network, and it doesn't matter if it's a wired network or a wireless network. We just consider all networks the same. We're only going to be able to see traffic that either comes down our cabling system or is visible to us in the normal environment. That traffic is going to be picked up by a number of tools, possibly. One of the tools is called WinPCAP, another one is AirPCAP, the third is LibPCAP. All of these end with the term PCAP, which means packet capture. So these are not just drivers, but they're also libraries that allow us to pick up these packets off the cabling system. Now, most analyzers run in what we call promiscuous mode. That means that we set our analyzers up so that we can listen to everyone's traffic, not just traffic addressed to our own MAC address. WinPCAP is the Windows packet capture tool. AirPCAP is a Windows packet capture tool for wireless communications. and libpcap is used on other OS systems. So the packets are picked up, and we can actually see that count of the number of packets that are visible to Wireshark, but it doesn't mean that we want to save all of those packets. And that's when the capture filters come into play. With capture filters, we can say that we only want to see certain types of packets saved in our trace buffer. For example, maybe we only want to save broadcast packets, anything going to the MAC address FFFFFF, FFFFFF. That's where capture filters would come into play. Now, once we've defined what traffic we want to see, what traffic we want to capture, we now pass that data up to the capture engine. Now, at this point, the traffic will stay there, and the next piece is going to be very important, where that gets handed off to. But before we look at what happens after the packet engine, or the capture engine, let's look at what happens when we pick up packets off of the hard drive, because it's a little different when we pick up the trace files and examine them off of a hard drive than when we're picking up the individual packets off of a network. When we open up trace files, we're picking up these files from a drive, and there's a piece called the wiretap library that is used in Wireshark. The wiretap library contains all of the information required to decipher these different trace file formats so that Wireshark can read them. There are a lot of different formats that Wireshark reads now. Let's go over to Wireshark and I'll show you the master list of all of the formats that it uses at this time. So I've got Wireshark open now, and I'm going to select Open a Capture File, and I'm going to select the files of type to show you, look how many different formats Wireshark recognizes at this time. And it's that wiretap library piece that makes it possible for us to read all of these different formats. So now we have the packets and they're ready for viewing, whether we've got them ready for viewing by the capture engine or the wiretap library. There it is coming into the capture engine. There we've opened up a trace file with the wiretap library. Now from this point, the packets will come up and be processed by the core engine. And the core engine piece is the piece that really holds all of the components together. It holds all the code together for Wireshark. There are several really important pieces that are part of the core engine, and those include the dissectors. The dissectors are basically our decodes. It's how we interpret the traffic. So when a packet comes in and it's addressed to port number 21, Wireshark by default will decode that and say that that's an FTP communication. And if that packet happens to have USER in all capital letters right after the TCP header, Wireshark will recognize that that is a command. User is a command. And the argument would be the actual username that follows that. There are some dissectors that are implemented as plugins. So you may also see in Wireshark that you have a list of plugins that are part of Wireshark. And now at this point, display filters can come into play. Because although the core engine has all of the packets saved in there, we might not want to actually see all of the packets. So we can apply display filters to the traffic that the core engine has. Now, the biggest part of Wireshark that makes it different from TCP dump or Snoop or something like that would be the graphical interface. Wireshark uses GTK, which is the GIMP toolkit, and that is a multi-platform toolkit for providing that interface. GTK offers a complete set of widgets for developing a GUI interface for all sorts of projects. You can find more information about GTK online at www.gtk.org. Now at this point I want to take you back over to Wireshark to show you where the plugins list is, and then I'd also like to take you out to the Wireshark.org page to show you where the developer information is and show you what it's like to read some of the Wireshark code. In order to find the plugin list, we can select Help, About Wireshark, and select the Plugins tab. And here you'll see the plugins. Now these are simply dissectors, and dissectors are often called decodes with protocol analyzers. And some of those decodes are implemented as dissectors. Now let's go to the Wireshark web page and I'll show you where the code is, and I'll show you how to read some of the code. Now we're on the main Wireshark website, and of course this site may change in its looks over time, but it's www.wireshark.org. And if you scroll down, you'll see an area there for the developer specifically. So I'll click on Developer Information, And there you'll see a note up at the top talking about getting the code. Now the main development branch is located at this link, which is anon-svn, which is ANONSVN dot wireshark.org/wireshark/trunk/. I'll click on that link, and now it's going to take me into a directory structure of the Wireshark code. Now the dissectors, the decodes, are available under the EPAN directory. We'll select that directory, and there underneath there you will see one directory called dissectors. We'll select the dissectors subdirectory, and now if you scroll down you'll be able to see that these are all of the protocols and applications that Wireshark can decode. So as we scroll through, here you'll see there's boot P. Scroll through a little further and you'll see there's Cisco, Daytime Protocol, DCE-RPC, Distributed Computing Environment, Remote Procedure Call. There's the DNS decodes. I'm going to take you to the FTP decodes. Now here you can see there's ftp.c. So we'll click on that, and you can see it explains at the top that these are the routines for FTP packet dissection. You can see who wrote this, who worked on this. If there's any sort of extra copyright information, you'll see it at this point. And then as we scroll through, you'll be able to see the code. And you can see these are, as you can tell, with FTP, these are the response codes that you'll get from an FTP server. 220, service ready for new user. That's what will precede normally a banner. User logged in, a 230, proceed. These are codes that we would normally see on the wire. So a lot of the code is readable, and it's very well documented. I'm going to go back now. I'm going to go to the dissectors for TCP, because TCP is an interesting one. Now all of your networks are probably going to have TCP traffic on them, but TCP is interesting because the expert system has a lot of information about TCP communications, and that expert system is actually held inside of the dissector. So I'm going to select packet-tcp.c, and here we are inside of the TCP dissector code. Now as we scroll through, the most interesting area is going to be the area that deals with the expert system. Here we can see a list of the expert notifications that Wireshark will provide to you. If you wanted to know more information about one of these, we could take, let's say, retransmission. And we could say we want to find the value retransmission. Don't do the underscore with that because you won't be able to find that. Here I'm in a section of the code that talks about what a retransmission is exactly. It differentiates a retransmission from a fast retransmission from an out-of-order packet. So if we need to figure out why Wireshark is flagging something in the expert system, one of the things that we can do is we can go directly into the code and read it to find out what the criteria is for putting something into an expert notification. So don't be shy about going into the code if you wonder how things are working. In the next section, we're going to look at Wireshark folders, more information about the plugins, and then we'll examine Wireshark help. As you work with Wireshark over time, it's going to be necessary for you to know where files are kept that relate to the interpretation of trace files, the default configuration, your personal configurations in Wireshark, etc. You can find that information by selecting Help, About Wireshark, and probably the main area you want to focus on is Folders. Now folders will say where your trace files will be saved by default. You can see on my system my trace files will be saved to the C:\traces directory. Here's my temporary directory, and this is where untitled capture files will be saved. You need to have a fair amount of drive space, especially if you're saving using a ring buffer and multiple files. In addition, you need to give Wireshark as much memory as you possibly can. Now the personal configuration information will be listed here as well, and it doesn't matter whatever operating system you're running on, you'll be able to get this information through Help and then clicking on Folders. The personal information would contain things such as my personal display filters that I added to Wireshark, my personal preference choices, things like that. The global configuration information for Wireshark is held directly in the Wireshark directory, and these are the things that we don't want to change. If you want to make a change to one of these things, those should be done in the files that are in your personal configuration directory. Now we also have the system and program information for Wireshark, which is sitting in the Wireshark directory. Plugins, personal plugins, and global plugins are also held in different directories. One would be in the personal plugins directory underneath the local logged in user. The other is directly under Wireshark plugins and then the version of Wireshark that you're running. Now I'm looking at the Wireshark directory, and here we can see there are a number of I have a couple of capture files that I saved directly into here for doing some tests, but you'll see some executable files, and all of those are the command line files. Now the command line tools with Wireshark are really nice to use. The top two tools that you'll probably use will be T-Shark, which is the command line capture tool, and possibly you'll use edit cap. So if you get a really large trace file, you can split it into multiple pieces. All of the command line tools are covered in section 11 of this course. Now in addition here you'll see the default set of capture filters, and you'll see the default set of display filters. Now these files are created just in a text format. I'm going to open my display filters default file just using WordPad. Now we wouldn't want to edit the file that's sitting in this directory because we would want to go to the personal preferences directory and change the file in the personal preferences directory. In addition, in this directory you'll see the list of the authors for Wireshark. So I'll open that file up. I'm going to open it up with WordPad. This is going to be the same list that will be displayed when you look at this information in the help area. There's also an FAQ document or a fact document about Wireshark that you can read here. The latest and greatest information that will be up online at www.wireshark.org. You can see by looking at this directory information that I've done an upgrade from WinPCAP 3.1 to WinPCAP 4.0, and when I went through the upgrade it left 3.1 in this directory, but I did upgrade to 4.0. Now let me take you over to Wireshark's help information. Just as with most programs, under help you'll be able to find the contents section there for a user guide that's contained within Wireshark. In this user guide you can get information on building and installing Wireshark and how the user interface works. In other words, all the menus and what each of the items inside the menu means. There's also a section on advanced topics such as following TCP streams, dealing with time zone issues and packet reassemblies and checksum problems. You also have a section there about customizing Wireshark, and that's one of the things I do recommend that you do customize Wireshark. You'll see later in this course that we talk about changing the preferences setting for Wireshark so that it's customized for your environment. Again, don't forget to go online to www.wireshark.org for additional information on how to run Wireshark on your network. There are a number of resources and references that everyone should know about whether or not they're using Wireshark if they're involved in network analysis. The main site would be www.wireshark.org, and that's where you'll find out information about how the development process is running. You can get access to the developers' information. You can also get on the Wireshark users mailing list from this location. Wireshark also has a wiki page where you can get additional information, and that's a place where you can find some extra capture files. So you can look at extra trace files that people have put up online. In addition, of course, we have the www.wiresharku.com page that deals with education and training on Wireshark, troubleshooting, network, and optimization. IANA.org is the Internet Assigned Numbers Authority, and that is one of the key places to go if, let's say, some traffic cruises across the cabling system and Wireshark doesn't recognize what application it might be based on the port number. If you need to look up the master port list, you can go online to www.iana.org and go to the Protocol Numbers and Assignment Services area to look up the port number information. IETF is the Internet Engineering Task Force, and that's where you'll go to find the RFCs, or the request for comments, that explain how so many of the standard applications run that are running over TCP/IP. In addition, online at www.packet-level.com, you will find a number of resources and articles and training information and trace files related to network analysis. And finally, you can get some additional trace files online at www.icir.org/enterprise-tracing. This site is the Lawrence Berkeley National Labs, where they have over 11 gigs of trace files for you to look through. So these are some of the key resources. And now would be a good time to pause the video and to go out to some of these resources and sort of check them off and recognize what you can get from each one of these sites. When you're going to use an analyzer to troubleshoot network performance, you always need to keep in mind how the data is flowing. And when you decide where you're going to tap in, you have to consider what's visible to you. For example, in a hubbed network, everything goes everywhere, but we don't often find hubbed networks out in the corporate world. In a switched network, we have to take into account the fact that only certain traffic will flow down our port. So we may have to make adjustments to make sure that the traffic we're interested in is visible to us. It's the same thing in a routed network, whether it's a local routed network or you have a WAN in there. But we need to make sure that the analyzer is placed in an area where we're allowed to see the traffic. And if we're not allowed to see the traffic, we've got to take some steps so that we can get in the path of the data flow. Now, in a hubbed environment, analysis is very simple. All you need to do is plug into any hub, anywhere, and all the traffic flows everywhere. Everything goes everywhere. Hubs are dumb devices. All they know are bits, ones and zeros, and they forward everything out every port. But nowadays you won't find too many hubbed networks around, so we don't get this luxury of just plugging in wherever we want. Most of the time nowadays you will find that you'll be working on a switched network. In this case, switches will only forward down to our analyzer station 4 different types of traffic. The switch will forward broadcast traffic, multicast traffic, traffic to and from the analyzer's hardware address, and any traffic to an unknown MAC address, a MAC address that hasn't been learned yet, which really isn't typical. We shouldn't see that. So if we plug this analyzer into this switch and we're plugged in on port number 1, the only thing we'll be able to see are the broadcasts and the multicasts sent by the clients and the servers on this network, and any traffic to and from the analyzer's MAC address. And once again, if by chance we have some traffic going to an unknown MAC address, the switches will forward that unknown MAC address traffic in hopes that they will learn which port that MAC address is associated with based on the response. So we have a problem when we go analyzing on switched networks. And most of the networks that you'll probably work on today are going to be switched networks. If we want to listen in on one of these clients communicating to the server hanging off of our switch, we'll have to make some adjustments in the way that we perform our analysis. One way to do this would be to hub out. And that's where we take the client's workstation and instead of plugging them directly into a switch, we plug them into a hub, and we plug our analyzer station into that hub as well. And then the hub itself gets plugged into the switch. Now, because hubs forward everything out every port, anything that goes to or from that client's port up to the hub will be copied down our analyzer port, and we can see everything that's happening. Now, this is one of my very favorite configurations for troubleshooting network performance. Ideally, you don't want to be sitting in the wiring closet very far away from the users that are complaining. If you can find one user who will allow you to hub out their traffic and let you watch their system as they're experiencing performance problems, you not only get to see what's going on the user's screen and see how the user deals with it and what they consider a delay and what they consider an outage and those kinds of things, but also all of your time measurements are done very close to the user. as opposed to being far away at the other end of a communication. So this would be the first thing that I would do if I were troubleshooting the network is slow problem. I would hub out to the client. Now, one of the problems that we have in hubbing out is that there are a lot of devices out there that you can buy that are called hubs, but they're actually not hubs. They're actually switches. And when you plug in what you think is your hub into the network, all of a sudden you find that you're only looking at broadcast, multicast, your own traffic, and possibly something going to an unknown MAC address. You're not able to listen in on the client's traffic. And that's because there are a lot of hubs out there that are actually switches. So what you need to do is buy some hubs, get some hubs at a store, take them to your lab environment, and plug in 3 systems. Your analyzer should be the first system, and then 2 other systems, test 1 and test 2. And if you can ping between test 1 and test 2 and have those two communicate amongst themselves or between themselves, and you can listen in on that on your analyzer system, then that hub is actually acting as a hub. But if you've plugged those 3 devices in and you can't hear test 1 and test 2 talking to each other, all you hear are maybe their ARPs when they discover each other's MAC addresses, then your hub is not a hub. Your hub is actually acting as a switch. Now, we have a number of hubs in our office that are known to be good hubs. We've tested them. They do very well. But we've found one exception, and that is when a known to be good hub turns into a switch because of speed mismatches, which means that it might be a 10100 hub, and if one system is plugged into it and syncs up at 10 megabits per second, another device plugged into it syncs up at 100 megabits per second, our hub, automatically turns into a switch, and suddenly we find that we're blind to the traffic. Obviously, this brings up a problem with the speed as well. Those systems should have been connected at 100 megabits per second. So watch for that. Make sure that you go out and find some hubs, you test them, and then you mark them that they are known to be good hubs. Now let's say I've hubbed out at the client and I'm looking at the traffic, and the client is trying to download some file, let's say, from the server that's hanging off of the other switch, the switch in the upper right-hand corner. And when we look at this traffic, we're seeing packet loss all the way through the data transmission. So the client asks for the file begins to download, and then all of a sudden we see that we've got packets missing out of the sequence. Now in step number 1, I want to be as close as I can be to the client to hub out and see what the client is experiencing, watch the symptoms. Step number 2 would be to go closer to the server and see, move upstream to see if the server was dropping the packets outbound. So the next step would be to move closer to the server. Now, it's very unlikely that somebody is going to let you disconnect a server from the network so that you can put your hub in there so you can listen to traffic. That is doubtful. So when we get to the area of going to a server or one of the critical devices on a network, and we need to look at the traffic to and from that machine, and that machine is hanging off of a switch, hubbing out is probably not the best way to go. In that case, we would look at doing spanning or mirroring, also known as mirroring. SPAN, S-P-A-N, stands for switch to port analysis. And that's where we go to that switch and we reconfigure it to say that we want all of the traffic to and from the server's port copied down our analyzer port. So now we're not being intrusive on the server. We do a slight reconfiguration of the switch, and now we can listen in to all of the traffic to and from that server, and we're looking for any packet loss at that point. Now, if we took the traffic down at the client workstation and we saw packet loss upstream, then we went up to the server and we did spanning on the switch to listen in on the server's traffic. And at the server side, we did not see any packet loss at that point. We see the server going through and sending the packets perfect sequence, and then periodically we see the client saying, hey, I missed something, but we saw the server send it out. Okay, now we know that the packet loss is downstream from where we are. Now we need to move and we need to look at maybe the port that's connecting the 2 switches together and span that port and see if we see packet loss from the port at the top switch going to the bottom switch, or sitting down at the port at the bottom switch to see if maybe we've already lost packets from that point. Now in the routed environment, of course, if we are sitting in the left-hand side of this picture and we're on network 10.1, and there's a router that separates us from network 10.2, we're not going to be able to see any of the communication between the devices on network 10.2 because that router, that layer 3 routing device there, will say that there's no reason 10.2 traffic should go over to network 10.1. So we won't be able to see it. So in that case, we would have to move over to network 10.2 if we wanted to listen to that traffic. If anyone over on the network 10.2 though is talking to anyone over on network 10.1, we can go to the switch and we can span all the ports down to our individual port, and that would allow us to see the traffic going between 10.2 network and 10.1 network. Be careful of spanning all the ports on a switch. You may overload your one port. So for example, if you have a 24-port switch and it's a very busy network, most of the ports are using, let's say at least 15-20% of the possible bandwidth on those ports, and you span all the ports down your measly little port number 1, you're going to overload your port number 1. You won't be able to catch all of the traffic in that communication. So be selective when you decide that you want to do port spanning. It's very rare that I'll ever go onto a network and say that I want to span all ports. Typically when you go into a network and there's a problem, you really focus on where that problem is. If every single user is complaining about performance, take one of the users that seems to be having the worst time of all and is very consistent and will allow you to hub out to their workstation, and start from that point. We really don't tap into very many networks and say, show me everything. We usually walk in a little more directed. In a full duplex environment, we would have multiple channels running from, let's say, a server to the full duplex switch. So we have a receive channel and we have a transmit channel. And you can consider those as two separate lanes on a road. The hub scenario that we were talking about in the last section will only capture on half duplex communications. So when we get to full duplex communications, we have to use something different. We would have to use a full duplex tap. Now this is a separate piece of hardware that you would purchase, and in a little bit I'll just show you what one of these looks like. In this situation, we pop in a full duplex tap, and yes, I have put it right off of the server there. I have some clients that have full duplex taps sitting in connected off of the server's link all the time, so they can go ahead and just plug in and listen at any point. And an alternate way of capturing this traffic would be to plug directly into the switch and span or mirror ports down to your workstation. But this is how you would plug directly into a full duplex communication. Now in the best situation, you would only have to have one analyzer hanging off of that tap. But unfortunately, if you go out and you buy a full duplex tap, there are two varieties there. One will require a single analyzer to plug in, and another one might require two analyzers to plug in. This is called a non-aggregated capture, and it requires the use of two analyzers. So here we have a server that connects through a full duplex switch, and the client would normally connect directly into that full duplex switch as well. But we've placed a full duplex tap along the client's path. Now this is a non-aggregated tap, which means that it's not going to send the transmit and receive channel information down simultaneously to a single device plugged in. Instead, it's going to have two connections, and you're going to have to connect two analyzers to the tap. Analyzer number 1 on the left-hand side would be able to listen to the traffic from the client going to the server. Analyzer 2 would be listening to traffic going from the server to the client. So we end up with two separate trace files. Now, sometimes we can analyze the separate trace files, and that's fine. We don't have to listen to both sides of the communication to understand what's going on. We can kind of infer that based on the traffic that we see. If you do capture this way on a non-aggregated tap, you might sometimes want to merge the trace files together though, so that you can see the full picture of the client and the server talking back and forth to each other. In that case, we take the two trace files and we merge them together. But it is very important that those two analyzers that captured that traffic were time synced. And this is when we set them up to go out to an NTP server, a network time protocol server, to sync themselves. And you want to point them to the same time sync server. That way when the packets arrive at the analyzer, the timestamp that's placed on them will allow them to be reassembled in the proper order. Now ideally, you will buy a tap that is an aggregated tap. It will allow you to do aggregated captures, which means that it will capture the bidirectional traffic and it will aggregate it. It will put it together at the tap and feed it down to your analyzer, all put together nicely in order for you. In other words, you get to see the client to the server communication and server to the client communication, just as if you were hubbing out on a half duplex environment. Everything will be ordered appropriately. Now on the left-hand side of this slide, there are three different pictures of aggregated taps. We have a gigabit copper dual port aggregator, so you have two ports that can come out of that aggregated tap. And we also have one for 10 base T. And then there's one that has just a single port hanging off of it, a single port for single port communications to pull the information off of that tap. These three taps are available from a company called NetOptics, and their website is www.netoptics.com.